So here we're trying to find the Fourier Series Coefficients for a sawtooth waveform, and I'm calling it a half-cycle sawtooth because we've got the sawtooth, but then we've got half the cycle that's 0. So the sawtooth bit is from 0 to t over 2, and then you've got 0 from t over 2 to t, so this bit is 0. And this is the linear bit, it's ax, so strictly speaking we should specify that as a times t over 2. So here we'd have at over 2. Okay, before we start, it's good to rewrite this in terms of theta. So theta is 2 pi x divided by t, where t is the period of the waveform, and here the period is in fact t. So generally for theta we like our waveform to repeat every 2 pi radians. So if t were 2 pi, we'd have theta equals 2 pi divided by 2 pi times x. So I'm assuming t here is equal to 2 pi. So now I can rewrite that as a theta, and then go ahead and calculate the coefficients. Now the coefficients have known expressions. So to find a0, it's just the average value. So the average value a0 is the integral of your function over one entire period divided by that period. So it's 1 over t, or 1 over, in this case, 2 pi, the integral from 0 to 2 pi of f of theta. And f of theta, because it's defined in over 2 regions, we've got a different expression for the linear part and then the 0. What we can do is split this integral into 2. So we've got the integral from 0 to pi, and then the integral from pi to 2 pi. So you've got the integral from 0 to t over 2, which in this case is pi, and then from t over 2 to t, in this case 2 pi. So I have 2 integrals. Now f of theta is either a theta or 0, depending on which region we're looking at. So in the question we're told that y, or we can rename that as f of theta, is either ax or a theta or 0. So I've replaced this with the expressions we're given, so that we don't need to integrate that because it's simply 0. And if you integrate a theta, a is just a constant, we can take that out. The integral of theta will be theta squared over 2, and then you substitute your limits, which in this case is not pi, it's not 2 pi, it's pi. So you just substitute your limits and then subtract. So the average power here is going to be a over 4 pi times pi squared minus 0 squared, and one of those pi's will cancel. So that now is our expression for a naught. Now remember, to find the Fourier coefficients, we need to find a naught, an for all the cosines, and bn for all the sines. So that's what we're looking for. We found a naught. Let's now look at an. And again, there is an expression for an. It's 1 over pi times the integral over one full period of your function f of theta multiplied by cosine n theta. An is the coefficient for the cosine, so when we integrate, we need to multiply f theta by cosine n theta. And again, because f of theta is defined over two different regions, I need to split the integral into two. So we've got from 0 to pi, and we've got the bit from pi to 2 pi, but that's just going to be 0. So there's no point calculating that. So what I'm going to do is focus on the bit that isn't 0, which is from 0 to pi. Now here, it's a less easy integration because you've got theta and cosine theta, and they're multiplied. And it isn't straightforward integrating theta cosine theta, or x cosine x. So because of the multiplication, because of the product, we're going to need some other technique, in this case, integration by parts. So remember the formula for integration by parts? So we're going to need to specify u and dv. So I've taken theta as my u and cosine n theta as my dv. And then you differentiate theta to get 1, and you integrate your cosine to get sine, but then you need to divide by the coefficient of theta, so I divided by n. And then the integration by parts rule says the integration of u dv, that's these two multiplied, equals uv minus the integral of v du. So what I sometimes do is draw a big capital N to remind me it's this times this, there, minus the integral of these two multiplied. And when you multiply these two, you end up with a sine. And even though we have an n in the denominator, n is a constant as far as the integration is concerned because it's d theta. And the integral of a sine is negative cosine. So the negative turns this negative sign into a positive, and that's my cosine. And then I divide by n, which is the coefficient of theta. And I already have an n, so we have n squared in the denominator. So the integral of theta cosine n theta is that. And I can then use that back in my original expression here. So this, this can replace that. So now, or maybe I can write it like this. So this replaces that. So now I simply need to substitute my limits and subtract. Now, even though we don't know what n is, we sort of know that sine any multiple of pi is 0. We know that because sine is 0 at pi, 2 pi, 3 pi, 4 pi, etc. So we know that sine any multiple of pi is 0, and obviously sine 0 is 0. So we really don't need to worry about that term. And cosine multiples of pi, it depends whether that multiple is odd or even. So for odd multiples of pi, so pi, 3 pi, 5 pi, the cosine gives you -1. And for even multiples of pi, cosine n pi gives you 1. So if you substitute, let's do the odd first. So for odd values of n, if you substitute -1 there, minus, and then you substitute cosine 0, which is 1, you end up with, if you include the a over pi, you end up with negative a over pi n squared minus a over pi n squared. And I'll do that again for even values of n. So you're going to have cosine even times, say n was 2, cosine 2 pi is 1, so that's 1 over n squared, minus, and then you put the 0 instead of theta, and you get cosine 0, which is also 1, so you end up with 1 minus 1, or in this case, a over pi n squared minus a over pi n squared, so 0. So if I simplify these, I end up with that. All right, so I have two expressions for a. One for odd values of n, one for even values of n. I could be clever and combine these two into one expression, but I don't need to. It's enough to say, look, an is this expression when n is odd and 0 when n is even. So that is an. Now remember, what we need to do is find a naught, an, and now bn, the Fourier coefficients. And now I'm going to start working on bn, and it's exactly the same. Same expression, except the cosine has been replaced with a sine. And again, we're going to split the integral into parts from 0 to pi, and then from pi to 2 pi, it's just 0. So we're going to focus on the first part of the expression. And once again, we've got this integral that we're going to need help with. So we're going to integrate by parts again. So I'm going to take my u as theta and my dv as sine theta, or sine n theta. I'm going to differentiate the theta to give me 1. I'm going to integrate my sine to give me negative cosine, and I'll divide by the coefficient of theta, n. And then we use the integration by parts formula, so the integral of u dv, this product, is equal to uv minus the integral of v du. And this minus with this minus will give you a plus there. Integrating cosine just gives you sine, and then we divide by the coefficient of theta, so n squared, because we already have an n. Now we found this integral, we can use that here and just replace that there. And now we're back to substituting the limits. And again, remember, sine any multiple of pi is 0, so you don't need to worry about that, because sine 0 is 0 and sine any multiple of pi is 0, so that's always 0. We need to focus on this. And again, for odd values of n, cosine n pi is minus 1, and you've got a negative there, so you've got a negative negative, so that gives you your positive. And when you substitute 0, even though that is a 1, you're multiplying by 0, so there's nothing really to subtract. So there's no point substituting 0. So that's for odd values of n. For even values of n, cosine n pi is 1, so that will be equal to 1. So we'll simply have a negative, and that theta will be pi, so negative pi over n multiplied by a over pi. So these look very similar, but one is the negative of the other. So we can say b of n is either a over n or negative a over n, obviously because we're cancelling out the pi's. So these are our b's. Now remember, the question was to find the Fourier coefficients. which consist of the A's, the B's, and the C's. So A0, AN, and BN. So that would be your final answer. So once you've found A0, that shouldn't be a multiple of n, or shouldn't be a function of n. AN, that will be a function of n, and in this case it depends on whether n is even or odd, and the same with Bn. So as far as I can tell, that's your final answer for the Fourier coefficients of a gated half-cycle sawtooth waveform.